Now let's look at this function f of x equals 1 over 1 plus x squared. And we'll go through the same steps that we did before, starting with step 1, where we determine the domain. For the domain, we need to take the denominator, set it equal to 0. That's 1 plus x squared equal to 0. But in this case, if we tried to solve that by subtracting the 1 over, and then we would be forced to try to take the square root. That's not possible in the case of real numbers. So there's no real solution to this instance here, which means that the domain is all real numbers. We could also consider that there's no way of getting a number for x and making the denominator 0, at least with real numbers, because if I plug a number for x in, it just gets squared and then added with 1. And there's no way to make that into a 0. Now, as far as the x-intercepts go, we can try to solve for that also. However, you might notice a pattern emerging here with these type of functions where there's not much in the numerator. I set the whole thing equal to 0. I get rid of the denominator by multiplying it to both sides, but the numerator doesn't have much to do. There's just 1, and I would say 1 equals 0. So in this case, again, there's no way of solving, and there's no x-intercepts. The y-intercepts, however, might fare better if we try to put a 0 in the place of x. We would get 1 divided by 1, or just positive 1. So the point 0, 1 is a location for the y-intercept. In case of asymptotes, the vertical asymptotes VA, where we take the denominator and set it equal to 0, but just as we saw up above, we can't solve. So that means there are no vertical asymptotes as a result. We can check out the horizontal asymptotes and see if anything happens there. In that case, we would divide leading coefficients when the powers on top and bottom are the same, but they're not in this case. In cases like that, I mentioned we can place a 0 placeholder term. So I'll put a 0x squared on top so that I then have appropriate leading coefficients to divide. 0 divided by 1 is 0. So it turns out we have y equals 0 is the location for a horizontal asymptote on this one. Okay, and now we're going to find the derivative. Let's start with our function here, 1 over 1 plus x squared. We're going to have to use a quotient rule again to find the derivative. So f prime of x is equal to low 1 plus x squared d high. Well, d high is the derivative of the 1, which is just 0. So that's low d high minus high, which is 1, d low, which is 2x, all over the square of what's below. Well, that's kind of cool because the numerator just simplifies to just negative 2x over 1 plus x squared in parentheses, all raised to the second power. So that's our first derivative. Now we'll go ahead and consider where the first derivative is equal to 0. So if we take the negative 2x divided by 1 plus x squared, all raised to the second power, equal to 0. We'll do that. We'll also consider where the first derivative does not exist, which again is going to be about the denominator equal to 0, regardless of what power it's raised to, just the stuff in the parentheses. Now we will get a little bit of different situation happening here with the derivative set equal to 0, because when I try to multiply both sides by the denominator and clear out the denominator and leave just the numerator on its own, we'll get negative 2x is equal to 0. So there's actually something to solve for x here, unlike some of the other instances we've seen. X will be equal to 0. We get a critical number. On the other hand, with the does not exist, we have another no solution case, just like the other denominators we tried to solve. So we do get one critical number, in this case the x equals 0. So we're going to set that up here on the number line. Pick out some test values. Picked out, in this case, a -1 and a +1. And let's plug those numbers in to the first derivative and see what happens. If I plug in the -1, we'll have 2 divided by -1 all over 1 plus -1 squared all squared. Let me highlight the number I'm just plugging in here. That's where I plugged in the -1. On top, I got +2 divided by +4. So it's a +1/2. Positive means this thing is increasing with the first derivative. For +1, we'll plug in the number here. And I came out with -2 divided by 4, or now -1/2. Negative means it's decreasing. Okay, so we can say here that it has decreasing on the interval from 0 to infinity, increasing on the interval from -infinity to 0. We do have a local max min in this case because it actually exists at x equals 0. In this case, this going up and then coming down is a local maximum for x equals 0. If we plug that number in, f of 0, back in the original starting function, we'll have 1 over 1 plus 0 squared, which is just equal to 1 divided by 1, or 1. So the coordinates 0, 1 are the coordinates of a local maximum here. For step 4, we're going to need to find the second derivative here. And that gets a little bit hairy because we just saw what the first derivative looks like. And in the first derivative, again, we had -2 over 1 plus x squared in parentheses all squared. So when I find the second derivative f prime of x, we could either rewrite it in a way to use product rule, or we could use the quotient rule. I'm going to go ahead and stick with the quotient rule again here. So we're going to go low 1 plus x squared in parentheses all squared, d high. Thankfully d high isn't anything too crazy, it's just -2. So low d high minus high, -2x d low. Now d low is going to be 2 parentheses 1 plus x squared raised to the first power times 2x. And that's a chain rule. That's how I got this information here, by taking the derivative of the denominator. All over the square of what's below, which means we need to take 1 plus x squared all to the second power and raise it to the second power again. And if we simplify this down here, we'll have -2 parentheses 1 plus x squared minus, or plus I should say, because we're going to have a negative here to get it turned to a positive. And then we have a 2x, a 2, and a 2x to multiply together. And those 2 times 2 times 2 is 8. And we also have x squared, parentheses 1 plus x squared next to it, all over 1 plus x squared raised to the fourth power, when we do the second power and the second power to get to the fourth power. What I would highlight here is the fact that both of these terms have a common 1 plus x squared, and that's also in the denominator. We can get rid of one of these completely here by reducing this fraction down on top and bottom. So I'll get to cross one out from the bottom, taking it from the fourth down to the third power. One goes completely away here, and one of these 2 to the second power brings it down to just the first power. So that would simplify it down to negative 2 parentheses 1 plus x squared plus 8x squared all over the denominator. Okay, I'll distribute the negative 2 into the parentheses, making it look like f double prime of x is equal to negative 2 minus 2x squared plus 8x squared on top. And that finally simplifies this thing down to 6x squared minus 2 all over the 1 plus x squared all raised to the third power. And that's our second derivative. We need to set that to the two checks here. First off, where the second derivative is equal to 0, or where the second derivative does not exist. It'll be easy for the does not exist situation here because, again, about the denominator equal to 0, there's no solution. That just carries forward from all the steps we've had above from the very beginning. So that really doesn't yield anything here. On the other hand, if we look at the second derivative set equal to 0, we will be able to find something interesting happening here. If we multiply and clear out the denominator to both sides, so let me cross that out here, it does leave us with 6x squared minus 2 equal to 0. If we add over the 2 and divide by 6, we would get x squared is equal to 2 over 3, or 2 over 6, or x squared is equal to 1 over 3. But that forces us to take the square root of both sides with plus or minus, just to bring it down to regular x equals. X equals plus or minus the square root of 1/3, which is not a very even number, let's say. It's actually a decimal, and I plugged it in and just took square root 1/3 in the calculator. I got 0.6, or for negative being approximately negative 0.6. Those are our only numbers that we got here from solving. Those would be our critical numbers in this case. So we're going to need to pick out the numbers on the number line accordingly to what we see here. So let me put down the numbers, the points, negative 0.6 and the positive 0.6. Let's pick some easy numbers to work with, as easy as we can. Say negative 1, 0, and positive 1. Those will be all our numbers for x. And we're going to plug those into the second derivative f double prime of x. Now, I won't bore y'all with all the details of plugging these numbers in. It's going to look a lot like the other things we've done, but let me do the first one. For plugging in negative 1, it's going to look like negative 6 times negative 1 squared minus 2 all over 1 plus negative 1 squared all raised to the third. And I'll highlight the numbers I plugged in there, the negative 1. The calculator will give us a value of 3 over 2. Being a positive value in the second derivative, it's concave up. Now for the value plugged in of 0, if you plug in the number 0, it'll actually, in the second derivative, it'll be equal to negative 2. A negative number means concave down again. And then finally, if we plug in the number 1 into the second derivative, it came back to positive 3 over 2. So back around to concave up again. So we can say this thing is concave up on the intervals from negative infinity to negative 0.6, union 0.6 to infinity. It's going to be concave down on the intervals from negative 0.6 to positive 0.6. Those two locations where it changes, we can call them the inflection points here because the function does exist, the first derivative and everything does exist for those values. So we have two inflection points here to deal with here. So let's write those down. The inflection points for x equals negative 0.6. If I go back to the original function f and plug in the number negative 0.6 inside there, let's see what that looks like. 1 divided by 1 plus negative 0.6 all squared. It's going to give us a value that I rounded to 0.7. So approximately 0.6 comma 0.7 is the location of the first inflection point. The second inflection point here, if we plug in the number positive 0.6 into the function, I rounded it also to 0.7. So also positive 0.6 comma positive 0.7 is approximately another location of an inflection point. Let's try to see what kind of graph we get out of all this stuff here. Going back to the very beginning, we talked about how there's a horizontal asymptote at the location y equals 0. We also had no x-intercepts, but we do have a y-intercept at y equals 1. Also, we talked about inflection points and local max min. It actually has a local maximum at the point 0 comma 1. And it has inflection that kind of works like this, where we had inflection points approximately at the points negative 0.6 comma 0.7 and positive 0.6 comma 0.7. So what's going to happen here is it's concave up until it gets to one of those inflection points, and then it switches to concave down, and then it switches back to concave up, making the graph look something like this.